Okay, sorry for starting a few minutes late, but it seems that even computer science students aren't completely tech illiterate. Is that better? Hux? Okay. Yeah, so Boolean algebra, that is today. So, what is it? Basically, Google is fun, but it says it's how you show relationships between entities and such. But also, it's just algebra. It's just algebra on certain things. Usually, if you did A-level computer science, you'll be used to doing it on logic gates and ones and zeros. If you're doing it here for the first time, all you'll know is about set theory and doing it on here. If you ever want to do questions online and you aren't comfortable on the different kind of symbols, just search up set theory Boolean algebra. It'll bring up a few more things than you need, but it will give what you need technically. Uh, there are, like I said, there are other symbols, but they all follow the same laws and logic, so there won't be anything different if you decide to do the logic side of things. Speaking of the different symbols, I have decided that everyone needs a table to help them out. It definitely comes in handy online, um, because there are tons of past papers for A levels with lots of Boolean algebra practice. If you want to practice using the laws, you've just got to use different symbols, and it's not too hard to sort of get done. I will, if anyone has any questions, please just do ask. I'm new to this whole presenting, obviously. Okay, so next slide. So the basic laws. These are ones that are generally common sense, and I won't be explaining too much. If you do want more explanations, please feel free to ask. I've got a paint tab open specifically so we can go through and see how they actually work. So first one, neutral elements. So when you have a union of the null set and a set, sorry, let me just describe what's going on in the slides. So up here, I don't know if you can see, it will explain what the symbols are. So A here is just a subset of X, and yeah, other slides will have other sets included as well, but for here it's just one. And then we have, I call them two different versions. We have it when it's the union and one when it's the intersection, so either way works. But starting off with the union of the null set, it's just A union null set is going to be A, simply because if you have A and you merge it with nothing, you just still get an A in the end. You just get out what you put in, which is what neutral elements are. When you do something to a set, nothing happens. And in logic, if you're more used to that, it's when you have an OR with 0, you end up with just, sorry, that's wrong, that should be N. Yeah. The truth table for that is below, which is just showing that in truth table, when n is 0, n plus 0 will be 0, when n is 1, n plus 0 will be 1. And then for the intersection, if you have A and you intersect it with its parent set, you'll just get A, because everything in A is also in the parent set, but anything that's not in A, that might be in the parent set, won't intersect, so it just throws you out A again. And again, if you're more used to the logic gate side of things and the logics, n and 1 will always give out n. So again, 0, 0, 1, 1. Next is annihilation, and this looks similar to the last slide if you can figure it out. It's just, instead of A union null, it's A union X, which will give out X. And this is basically when you merge A with its parent set, you just get the parent set, because nothing that's in A won't be in X, so it's just X is what you get out the end. And again, the same with logic. N or 1 is always going to be equal to 1 because there's always a 1 in there, so that's a tautology, always valid. And I've made another mistake. I apologise. I was doing this last night, but that's meant to be the null set. I don't know what it's saying, but okay. But yeah, no, that's just meant to be null. Okay, so that means if you have an intersection of A and nothing, nothing's going to intersect because there's nothing to intersect. So you end up with nothing always. And I cannot remember what the opposite word for a tautology is, so it's just the opposite for that. So you end up with zeros consistently, and again, n and 0 is always going to be 0. I made a lot of mistakes when I was writing this yesterday. Oh well. Sorry about that. I will correct as I go along. Okay, next one. Commutativity. I have no idea how to say this. Here we're using A and B, and they're both subsets of X. So when you have A and a union B, it's the same as B union A, and the same with the intersections. Where you have A intersect B, it's the same as B intersect A, and all it's saying is that the order of a function doesn't matter. So if you have either way round, will give you out the same output, whether it's an intersection or it's for a union. It doesn't really matter. Next one, idempotence. Again, here's just A is a subset of X. This just means that a set with a union of itself is going to be itself, and a set with an intersect of itself is going to be itself. This helps so much when you're trying to solve things down, because you'll have really long lists of stuff, and then in the end you'll get like A union A or A intersect A, and you can just squish them together and you end up with A by itself, and it makes your life so much easier. I can definitely vouch for that. So that's sort of the basic laws. Is there any more is there any questions about any of that? Yes, no? Post if you do have any questions, or you don't, please. We'll go into that. That was the quick stuff. That was like going over quite fast. Okay. Okay. So Ivan, it doesn't make sense, or is it just? Okay, so moving on. Next one is, these ones are a bit more complicated and they may take a little more thinking to get through. Realistically, there's no issues, and I do apologise from here on out. There is one or two screenshots from the lectures, simply because I think in the last few bits I thought I'd have a bit more time in between the last lecture, but they were a little bit rushed, so apologies for that. So first off, we have absorption. When you have it's theoretically it's just you're basically expanding out from. Have I messed up? I feel like I've messed up. No, I haven't. Okay, so absorption is what's it called? When you're it's similar to expansion, but it's not. It's when you have a specific set that just outputs the final set. So you basically put in two sets, and you basically A union B will intersect with B, and that throws out B, but then A intersect B. Yeah, it's a special case of expansion that results in a particularly simple output. I couldn't word for a second. The logic tables down here make it seem easier, but the best way to describe this is what they did in the thing. So they drew it up and they highlighted everything, and that's what we're going to do. So if you give me 30 seconds to open up the right thing. We're just going to here we go, Untitled Paint in Brave, go live there. There we go. And let's change OBS as well. There we go. Okay, so okay, for absorption we have two things. We have one sec, let me just make sure. Okay, so for absorption we have A union B, and then you intersect with B. So for A union B, we're going to say okay, so A union B is just everything in the set in its entirety. Let's actually just add a box around this, make it a bit easier. So that's A union B, it's everything in there. There's nothing else that's not going to be in there. So we then have to intersect this with just B by itself, which will end up, how do I, oh, colours, there we go. Edit colours. Okay. And then it ends up just being B, because the intersect between B and B union A is, in the end of it, just B. Does the intersection distribute over union? That's the next thing we're going to do, Hux. That's yeah, that's the next. That's distributivity. So that's basically expansion of brackets. This is simplifying. The next one's technically expanding. So so that was, if you saw, that was the first one. That was here. So that one was A union B intersection B, ends up just being B. And here, go live. And the next one is A intersection B is the same as A intersection B union B. So let's undo all of this. Okay, so it's blue now, lovely. Okay, so so A intersection B will end up just being this bit in the middle here, and then you have a union with B, which just ends up being the rest of this B here. So in the end, you just get out B. It works the other way around as well. If you have B intersect A union A, it ends up being it just ends up expanding out into A. Does everyone understand that? Because that's the easiest of the slightly more complicated ones. Or does, yep, okay. So next one is, so that's sort of, oh, I forgot to mention that, sorry. Here we go, back up to here. So Shay mentioned that, sorry. So if you can see my, you should be able to see my PowerPoint now. On my table I've got a whole bunch of different symbols. So the union is basically the same as addition and the OR gate. Intersection, I'm not sure if anyone's familiar with that symbol, but it's also the multiplication symbol. Usually in high level maths you use a dot instead of a x, because you're using so many different variables that x pops up so often. But no, intersections can also be multiplication. You can think about it like that. And then nothing's the same as zeros, parent sets are the same as ones, complements are sometimes have little hats on them. Personally, that's the way I like doing it, but everyone has their preferences, or the negation symbol shown before. But yeah, no, I will be posting this later on. If you want that table to do questions online, it's up to you. Okay, distributivity. This one is a little more complicated to prove, at least. It's simpler in aspects because you're all used to this. But yes, Hux, this is what you were asking about previously. If you have, let's say, 3 variables, it's the same as saying A plus B brackets multiplied by C you can expand that out to say A times C plus B times C. It is, in essence, algebra. That's all you're doing. You're expanding brackets, and I hope most of you know how to do that, because it's honestly not too bad or hard to do. And again, logic. This is the table to prove it. So you do all of you know how truth tables work, or do I need to sort of describe them in a bit of detail? Because I find truth tables make everything a lot simpler, but it's up to you. Do you guys know how it works or no? Okay, that's fine. I just want to make sure. Okay, so this is the truth table for this one. Sorry, this one is the truth table for this one. It just makes, personally, it just makes it seem a lot easier, but you can also use it to prove. So if you see this column is then exactly the same as this column, which shows they're exactly the same. Now, over into Paint. Oh, no, that's not what I wanted. 1 second. There we go. Go live. Okay, so in Paint now, we need a third circle. We have C. Yay! So, okay. Oh no, did I forget to switch back? Oh well. Okay. Okay, so C we have here now. So here we have is, the first thing we do is A union B, which is going to be all of that. A union B is all of this. And then we have to intersect it with C. So all of this intersected with C. Edit colours. Let's just go red. All of that intersected with C is just here. This little weird shape down here. So yeah, that's what we get. And then if we do it the other way around, and we have A intersection C, which is this bit, union with B intersection C, which is just this bit, and you see we end up just getting the same little circle, just through two very different methods. If my voice does go quiet at any point, just please let me know. The mic I'm using is obviously not the very best. Okay. Alright, let's now swap back over to Boolean Algebra. Yeah. Okay, so we're here. Let's swap OBS back to here as well. Okay, so that was when you have a union and an intersection. That's what you're used to. You have pluses and you expand with the multiplications. This one's a little different. You expand it in the same way, but if you were to write it out like an algebraic equation, it wouldn't look right, because you're expanding with the pluses instead of the multiplications. But trust me, it does work. The truth table here proves it. So as you cycle through, this column is exactly the same as this column. I won't be running through any of the truth tables, simply because usually they're just there for proofs and they're pretty self-explanatory. But now, so it's similar to the other distributivity, but it looks weird when you do it yourself. If you were to do it, it definitely looks a bit unique. So back to the MS Paint, because who doesn't love a bit of MS Paint? But online, because OBS decided MS Paint wasn't a real thing. Don't ask, I don't know. OBS, here we go. Okay, so here. So first off, we've got A intersect B, which is just this bit in the middle here, and we union it with the entirety of C, which is all the way down here. Let's see, actually. Can I copy this? Wait. And then CZ. Okay, there we go. That's a good idea. So that's what we had before. That was A intersection B, and then union that with C. And when you expand it into the other side of things, you have A union C intersectioned with brackets B union C. So the first thing we have is so first off we have is A union C, which is, sorry, give me a sec, is all of this. And then change colours to cyan again, and then B union C is all of this. Now we need to find the intersection between them, and the intersection between them turns out, let's say pink this time, why not? Turns out to be this bit here, all the way around here, down round here. So it's this little loop here, and that's exactly the same as what it is over here. Any questions for this one or the previous one, or no? Again. No? Okay, all good. I apologise for the next few bits. I have basically dragged them off from the lecture 6 notes. I was running a bit out of time with it because I too needed a bit of a break after the behemoth that was the session before, and oh my god, that was good. But here we go. If we change it back to here, okay. So I know it just looks like I've taken it from there, but I am sort of explaining what's going on. So complements and negation. Negation is basically everything that's not part of it. So if you say not A or complement A, it's everything that's not A, which should be common sense. But you have A unioned with not A, and it's going to be true consistently, because, or it's always going to be the parent set, sorry, I'm used to, anyway. So because if you think about it, if you have the parent set as X and you've got a little subset, you have A and everything that's not A. There's no sort of way about it. And the other one is sort of the intersection between A and its other set is nothing. I'm going to sort of pop over into Paint to prove this in a second. But yeah, it's not too bad. But then double negation. This one is definitely one of the most handiest rules. I will pop over in a minute to prove the other two as well. But double negation basically states that not A is going to be A, or the complement of A is going to be A, because as everyone knows, two negatives always make a positive, no matter the scene. Do not take that into real life, please. But okay, here, let's see. Okay, let's just get rid of everything for now. Okay, so we have the box, we have A, and okay, X, and this is A. Okay, so here we go. So so this is A, and everything outside of it is not A. So this is all not A. Everything still within X is not A. So the union between everything outside of the box and everything outside of the circle and the circle itself is just X, the entire container. Whereas the intersection between them, well, there is no intersection. It's either in the circle or it's out of the circle. You either have A in the circle or the complement of A out of the circle. So it's always going to be the null set, which is again nothing. And again, the complement of A, a double negation, is two things back to back, which is just going to end up being A. Okay. I apologise if the recording doesn't turn out so good. It's just probably going to be the pinging between slides that catches me off. Okay. Did everyone see that all right? And anyone have any questions? Because I just drew something in Paint and I can't remember if it was there. Okay. If no one's... Okay, that's fine. Okay. So, De Morgan's Law. Am I in the right... Yeah, okay, I'm in the right thing. De Morgan's Law. In the most simple terms, you're flipping everything. You don't like anything in whatever you do, and you flip it. In algebra, you can probably most think about this as timesing everything by -1. But basically, in layman's terms, you take a section or the whole equation and you flip everything, which results in you add a complement / negation to both sides of the equation, and you change the union to the intersection and the intersection to the union, which doesn't sound too hard until you put it into practice and you have about 6 of them in a row and you miss a step and everything goes horribly, horribly wrong. For this one, is there any point in me doing set theory for this, or would people just prefer some practice questions, me going over with this one? Because at least with De Morgan's Law, it's probably best to do questions like this. I do have questions set up we can do, but it's up to you guys. I can end the stream and post the questions, or I can do 1 or 2 questions with everyone. Okay, Shay's nominated for a few questions. Do you know what we're going to do? We're going to go back to Paint. Should be fun. Okay, change windows to Paint. Okay, go live and change this one here. Okay, so let's get rid of all of this and open up my questions. Okay, here we go. Yeah, okay. So, you all still with me, or have you all fallen asleep? Because I don't blame you either way, honestly. Okay, so change the colour to black because we're going to do some actual work now. Okay, so we will start with A intersection B complement, and then we union A. I apologise, this is not on a drawing tablet, I am doing this with a mouse and keyboard. Get angry with me all you want, I don't have the money for a tablet. Okay, so the first thing we're going to do here is yeah, okay. First thing we're going to do here is apply De Morgan's Law to colours. We're going to apply De Morgan's Law to this bit here. So it's when we apply De Morgan's Law, we'll take it, and since the complement's on the outside, we'll also add another complement. We will also add another complement, and then because double negation, where 2 negatives equal a positive, the complements cancel out. Then inside we will have a complement and B complement, and since it was an intersection here, we'll have a union here and a union of A outside, because we did not apply De Morgan's law to that specific thing. Okay, and from here we can then go back and think about our laws of associativity and say that commutativity, where, sorry, not commutativity, commutativity? I feel like I've missed something out. Have I messed up? One second, have I missed something? Did I forget associativity? I did. I had that slide up as well. Oh my god, okay. I had a slide all prepared for associativity. That's not good at all, is it? Sorry about that. I had it up and ready. Okay, so associativity, let's just quickly pop back. But in essence, I did completely forget. I made a slide, I remember making the slide, and I can announce word for word what I said in it. But, okay, let's go back to... So I don't know what happened to associativity, but it was here when I was watching the slides before, so magic, it's gone. But associativity is... Okay, it's similar to commutativity, where it doesn't matter if you have consecutive unions or intersections, so one or the other, it does not matter the order in which you do them. So you can have A, U, B, U, C, you can do B, U, C first, or you can do A, U, B first. Either way works, and it works the same way round as with intersects as unions. Okay, back to the paint. Sorry about that. I apologise. It was there in previously. It was previously there in my PowerPoint. I don't know where it's disappeared to. Okay. So we use the law of associativity. So we can then say that you have B complement, A complement, and A, the unions, you have it here. And as we all know, the union between A and not A is always due to annihilation. Wait, not annihilation. Sorry, is always due to complements X. So B complement union X. Yes, I am still sharing paint. Is it? Yeah, no, yeah. I just pulled up the PowerPoint so I could see it quickly. But yeah, no, so B complement union X is just going to be X, because anything that's a union with X is going to end up being X, because everything is a subset of X. So in the end, the answer to this one is X. Does anyone have any questions about this? Yes or no? No? Okay. Do you guys want to do another question, or do you want to leave it here for today? I'm still happy to post the I'm still happy to post all the questions I've got. They will be there from an A-level physics and maths tutor, and it's just me swapping the symbols around so you guys can understand a little bit easier. Yep, I can still post some questions after. I understand everyone's a bit tired, but no, so that's it. I apologise for leaving out associativity, but it was one of the basic laws, and it's something that no one should really have any problems with. Okay, nope, that's it for today. I hope you all enjoyed it. Well, enjoying it as much as you can. I'll post this and get it all sent out, and I'll see if I can get my associativity slide back. If not, there's no big ways either way. Thanks, Witty. Right. Have a nice night. See you guys. Wait, should I not have ended? Oh well. Okay, stop the recording.